Hello, everyone. My name is Sarika. I'm storage performance engineer with Intel Corporation. When we first started using DAOS for reference storage platform project, we measured 4K IOPS to be capped at about 10% of the expected performance. Today, I'll walk you through the reference storage platform performance and how it has evolved since those early days. I'll start with an introduction to the reference storage platform itself, and then we'll move on to the performance evaluation for bandwidth in IOPS, read quality of service, and read quality of service in presence of write. The reference storage platform is a learning vehicle for us. We built it with the goals of identifying storage performance bottlenecks and optimizations, as well as understanding workloads with platform changes, and to verify various hypotheses and assumptions of improved ingredients at platform level for cost and for performance. Reference storage platform itself is a storage platform. We are using DAOS as storage software stack. We're currently using Intel Xeon Gold CPU in a Cascade Lake system in 100 gig NIC. We have Intel Optane persistent memory on each socket. The drives that we used for gathering performance are Intel's 3D NAND QLC drives. And the data that I'm presenting today in this presentation was collected using FIO. On the right, I'm showing the picture of the platform itself. You can see all the components in the platform, pretty standard Cascade Lake system. So moving on to performance improvement over time, let's take a look at bandwidth and IOPS. The chart on the left shows bandwidth evolution from DAOS 0.8 to DAOS 1.0. And you can see right from the start, we were able to saturate 100 gig network link with DAOS 0.8 through DAOS 1.0. Going from DAOS 0.91 to DAOS 1.0, we moved from single socket to dual socket, and the performance scaled with hardware scaling. So pretty, uneventful story for bandwidth saturation for read and for write. However, when you look at IOPS, it was not that straightforward. When we started, we were capped at 100K 4K IOPS, which was about 10% of the network link. And then going from 0.8 to 0.91, we saw significant improvements in the read and the write IOPS, about 6x improvements for read IOPS and 4x improvement for write IOPS. With DAOS 1.0, performance scaled 2x when we went from single socket to dual socket. And for read IOPS, we were also able to get additional gains from DAOS stack improvements, and we achieved 100 gig link saturation by getting 1 million read IOPS. So we maintain a separate non-production DAOS branch with all the stack changes. Most of these stack changes have already landed in the master. There are a few changes that I understand are under validation and will be released after they have been validated. For write IOPS, although we are still capped, and we're working very closely with the DAOS team for improving the 4K write IOPS. So moving on to quality of service, the end user goal for us is to have Optane-like write latencies and NAND-like read latencies. What you're looking at is the tail latency chart with latency percentile on y-axis and latency in microseconds on x-axis. The latency percentile indicates that a given percent of I/O was below the charted latency value. If you have longer tail latencies, it can cause a suboptimal user experience or timeouts, and which in turn could result into retries and increase the I/O requests that are targeting a given system. What tail latency captures is the responsibility of the platform, as well as how predictable the performance is going to be. We saw a significant improvement in read tail latencies with DAOS 1.0, we saw about 800 microseconds of improvement for 5 nines of latency and 100 microseconds through 100 microsecond at 99th percentile of the latency for the reads that came from NAND after the content was destaged to QLC. And also, if you look at the lines A and B on the leftmost chart, you're looking at performance improvement that came from DAOS stack from Optane-based read caching. So that was, we saw a really good improvement with the latest code base that we have for read TailLatencies. For writes, we did not see significant improvement. As I pointed out earlier, we are capped at write performance since 0.91. So we did not expect a huge improvement, as well as for writes, note here that the writes are serviced with Optane DC persistent memory. So it does not target the backend storage. In absence of the Optane memory, you would see the NAND latencies that are shown in the chart on the right. So transitioning to read quality of service with write pressure, without responsiveness, IOPS or transactions per second cannot be utilized by the application. There are many ways to achieve transactions per second, but without the right latencies, it's not helpful. We saw a significant improvement in transactions going from 500 megabytes per second to 2.5 gigabytes per second with DAOS 1.0 with their performance patches. And you're looking at the keep out zone. So keep out zone is defined by the CSP read quality of service specification, where they expect 3 nines of latency to be less than 1 millisecond and 5 nines of latency to be less than 5 milliseconds. As your latencies start creeping out in the keep out zone, the system becomes highly unpredictable, and applications are not able to make use out of your transactions. So these experiments comprised of capturing the read latencies while driving write pressure. And you can see the difference between the chart on the left and the chart on the right. We were able to pull out the latencies from the keep out zone, and there was a 5-fold improvement in terms of how many transactions we were able to drive. And lastly, I would really like to thank for a close collaboration and support from DAOS team. They have been astoundingly helpful in the support they have offered to us, and we could not have achieved this level of performance without their help and support. Thank you. That's all I have. I'll take questions if there's time.
Sarika, this is Sylvia. Can you go back to page 4, please? Perfect. This one. So it does look like there's quite a bit of improvement going from DAOS 0.8 to 0.91 to 1.0. And I did hear you mention that the testing that you were done is off of a separate branch, right? And then,
Yeah.
a lot of the patches has been landed on a master. So just out of curiosity, is there any plans that, that we would want to do this sort of testing on a regular basis against master and to keep track of, hopefully we have a trend going up and not down. And if it goes down, at least we flag it right away and take a look what might have gone wrong. And any plans to do that?
Yeah, so we're already working with the DAOS team, and in fact, we have been working on integrating what testing my team does with the DAOS's testing test suite, and Johan can speak more to that. But there are plans to integrate this testing into DAOS team's validation.
Okay, perfect. Now, how about go to one page forward to page 5. Yeah, so I don't fully comprehend the whole concept of this tail latency thing. So can you explain a little bit more? And is there a way to take out like is it because of an outlier of a process that's not performing as well as the rest that is affecting the overall performance that you're seeing? And if it is there a way to exclude that and see how it actually compares with the majority of it?
Mm-hmm. So certainly, think of tail latencies as so if you're looking at this chart, right? On the y-axis, you're seeing the latency percentile, and you see the charted value on the graph. So when you look at this value, what that means is that 99.9% of the I/O had this latency or lower. It is not an indication of the average latency. If you look at the average latency, it's going to be much lower than what you see your tail latencies to be. And so if you want to look at average performance, you would be looking at the average latency. What tail latencies tell you is that for, let's say, in 1 in 1,000 I/O at 3 nines of latency, you're going to see this kind of latency, right? So if you're, for example, if you're accessing web pages, right? So let's say you have 1,000 users who are accessing your website, and they want to 1 in 1,000 person accessing your website is going to experience this kind of latency, right? When the numbers are small, this doesn't really make a huge impact. But when you're talking of millions of users accessing, several hundreds of pages per user, these start showing up. And what that leads to is basically some applications will have a higher tolerance, while some other applications will be very time sensitive, and they will time out that I/O, which then leads to the client generating more retries, and that loads your system up. So if you imagine millions of requests getting retries, you're increasing it by that many more I/O requests per request. So it gets out of hand very quickly. And so when you're talking about tail latencies, this is what CSPs will use to provide to their customers, and they use the term service level agreement. So these are baked into their service level agreements, is that at no point you will see more than, let's say, 10 microseconds latency for 99.9 percentile of your I/O. So that's the concept of the tail latency.
Okay, I see. So does that mean what would be ideal is that the two lines are parallel?
What would be ideal is, you do not have the longer tails.
Mm-hmm.
And two lines, you cannot have two lines in parallel, because these are also dependent on the characteristics of the storage itself, right?
Mm-hmm.
This was our previous generation NAND, QLC NAND SSD, and it had certain characteristics. And then this is the latest generation. On top of that, you are also talking of the DAOS stack latency.
Mm-hmm.
So ideally, if you want a perfect use case, you're going to have a vertical line.
Mm-hmm.
But that is not always the case, because there could be, various bottlenecks in your entire stack that is going to pull these latencies on the right as you go up. So you are going to see those longer tails, but the ideal case would be, yes, a completely vertical line.
Okay. Yeah, thanks.
Thanks.